Good afternoon, everyone. Today we're going to solve for n in this exponent, given this kind of messy looking bunch of radicals all bunched up together. And we're just going to use exponent laws, okay? So, first things first, let's remind ourselves of how radicals and exponents are linked. If we have the nth root of x to the n, which is the nth root of x all to the n, these are the same things. These can both be written as the nth root becomes the denominator of the exponent, right? So the number of the root we're taking becomes the denominator in the exponent, and the normal exponent serves as the numerator in our exponent, okay? So with that exponent law fresh in our minds, let's rewrite all of these radicals as fractional exponents. So in this first part, I'm going to write the cube root of 2 to the 7 as 2 to the power of 7 over 3. Okay? Again, the cube root means a denominator of 3 in the exponent, and a 7 means a 7 in the numerator. Okay? And now let's do the same thing for the others. So we have 2 to the power of 3 over 5, all over 2 to the power of 14 over 15. And this is still, in the end, equivalent to 2 to the power of n over 2. Now, we have our exponent laws that say when we multiply by the same base, we can add the exponents. And when we divide by the same base, we subtract the exponents, right? So really what we're dealing with here is a little bit of an exercise in fractions. We have these two exponents being added up because we're multiplying, and then we're going to subtract this fraction. So really, we are looking at 7/3 plus 3/5, adding the exponents through this multiplication, and we're going to subtract 14 over 15. Okay? Now, I trust that you're all familiar with fractions, so we know to add and subtract, we need a common denominator. For 3, 5, 15, clearly that common denominator is 15. So I'll do this times 5 times 5, and this one times 3 times 3, and the 14 15s we can leave as it is. So we get 35 over 15 plus 9 over 15 minus 14 over 15. And now with our common denominator, we don't add the denominators, right? They're 15s. We just count the numerators, and so 35 plus 9 minus 14 leaves us with 30 15ths. And now we know 30 15ths is the same as 2. So that means that all of this, through exponent laws, simplifies down to 2 squared, the exponent of 2 on the 2, and now that's equal to 2 to the n over 2. And now, since, let's get Robert here, since we have the same base on both sides, that means the exponents must be equivalent, and so that leads us to the fact that this exponent must be equivalent to this exponent, and so we get the equivalence of 2 is equal to n over 2, and now we're just about done. Multiply both sides by 2, classic algebra, and we get n being equal to 4. Okay, so I hope that helps. I hope that kind of helps de-amplify how messy these things can look at first glance. You know, we know that we can always change our radicals into exponents. You're probably more familiar with exponents, so that might be a good idea. And then using our exponent laws to always simplify down what we have to work with, and then using an equivalence argument to equate the two exponents, allowing us to solve for n. Okay? Again, I hope this helps, and thanks for watching.